So we left off finishing this proof of theorem 2. Let's just do a quick recap. Or was it the lemma? No, it was the theorem. We didn't prove the lemma. There's a lot of mechanical stuff done in the lemma that you can kind of check out. The argument in theorem 2 is a little more accessible, a little simpler concept, but I didn't show all the steps. So you want to go and see what basically occurs. So essentially you have a solution, you substitute in, excuse me, and you can solve this system because it's just a linear system. And basically you're using like Cramer's rule, or you're just solving it. You get C1 and C2. So if you go to page 162, you'll see that you have C1 equal to something, and then and what it's divided by is the Wronskian of y1 and y2. But because we're assuming that y1 and y2 are linearly independent, that'll never be zero. That's the key to that concept. Okay, so check that out. Some kind of good stuff in there. And then we go on to the next part. All right, so let's go on to distinct, meaning like only one. It's like they're different than each other, right? That's what we mean by distinct. Real roots. The characteristic equation has distinct real roots, R1 and R2, meaning they're different. Then both of those are solutions to our normal equation, and that the constant times the sum is a general solution. So that's what we essentially are showing above. For repeated roots, like you factor and you get like x minus 5 squared, then that's what this one says. So if the characteristic equation has a repeated root, then y1 r of t and y2 t e to the rt are also our solutions. And then that sums a general solution. Okay, so you can look at it. I'm not going to go through that proof. We can get bogged down in all this stuff we really wanted to. Let's look at an example. So let's look at number 20 from the book. All right, so solve y prime minus 4y prime plus 4y equals 0. Initial conditions is, kind of simple. Y of 1 is 1, y prime of 1 is 1. Okay, so let's go ahead and solve this. All right, so then let's do the auxiliary equation. So the auxiliary equation is r squared minus 4r plus 4. All right, so how about that factor? That would, of course, factor the r minus 2 quantity squared. Okay, and then the repeated root is r equals 2, of course. And we also call that, a repeated root, we also call like a multiplicity greater than 1. So repeated root, in our case, because it's only a quadratic, meaning it would be just 2 of them. It'd be multiplicity 2. So we also call that multiplicity. Usually when I teach, I use the p for like plicity. P is equal to 1. 2. Multiplicity of the root. Okay. All right, so thus, by the property above, the two The two linearly independent solutions are y1 of t equal to e to the 2t, and y2 of t equal to te to the 2t. And the general solution is y of t equal to C1, I just factor this, but C1 plus C2t e to the 2t. So, given that we have initial conditions, we can solve that for C1 and C2. Okay, so now find C1 and C2 by using the initial conditions. So I'm trying to give you, an explanation of all this once at least by using the initial conditions. All right, so what we have then is y prime of t is then equal to 2c1 e to the 2t plus c2 e to the 2t plus 2c2t e to the 2t. And that's just substituting into the equation and then solving it, basically. Because then I'm going to factor, that's 2c1 plus c2 plus 2c2t, factor out e to the 2t. So now substitute in, right? I just found my solutions here. This is my y. So y double prime, I'm plugging in those products, or those derivatives to each one of those, and then just y. And now I'm going to evaluate at 1 and solve for C1 and C2. You'll have to solve a system of equations, basically. All right, so then, so let's see if I can fit it here. Let's just go down here. So y1 is C1 plus C2, times 1, e to the second, and that's equal to 1. Okay, we'll solve that, or simplify, and y prime of 1 is equal to 2c1 plus c2 plus 2c2 e squared, which is equal to 1. That's what's given, right? Those two initial conditions are given. And there's only two unknowns, C1 and C2, so you don't need y double prime, right? Does that make sense? Like you only, and that's in the theorem and in the derivation in this type of case. I think it kind of has to do with this being 0, kind of degrees of freedom sort of thing. And so you only need to find initial conditions for y1 and y prime. I'm not going to get into that too much. Let's just kind of roll with this. So you can solve that now. And we have, so now you set up a system. So the system would look like this. C1 e squared plus C2 e squared equal to 1. And then 2 C1 e squared plus 3 C2 e squared equal to 1. Okay, so solve this system. Normally, the easiest way on a 2x2 is elimination process. So if you're not familiar, it's been a while or whatever, to solve linear systems of equation, good thing to review. Okay, so this is called a linear system of equations. If you have taken linear algebra, you know exactly what's going on here. But you don't need it. It's just, this is actually prereq simple algebra type stuff. Let's go ahead and get e out of there. So you'll get C1 plus C2, and I'll write that as e to the negative 2. Because you're just dividing by e squared, right? And then 2C1 plus 3C2 equal to e to the negative 2. So now here's your system you're solving. And I'll work this one out all the way this time. All right, let me go ahead and give myself some more room here. And we'll bring it across like that. I grabbed too much there. Let's try that again. All right. Okay, so we're just going this way. So first case, we're going to multiply by negative 3 right here and add to get that to cancel. So this is elimination method. So you get negative 3C1 minus 3C2 equal to negative 3e to the negative 2. And this is just 2C1 plus C2 equal to e to the negative 2. And then we add that up. And we have negative C1 equal to negative 2e to the negative 2. So then C1 is equal to 2e to the negative 2. Okay, then 2. Negative 2C1 minus 2C2 equal to negative 2e to the negative 2. 2C1 plus 3C2 equal to e to the negative 2. So multiply equation 1 by negative 2, multiply through, simplify or add now. So if you add that, you get, well, that one's nice, huh? That's just C2 equal to e to the negative, e to the negative e to the negative 2. Negative e to the negative 2, okay. Okay, so we found C1 and C2, so therefore we have it. So therefore, the solution is y of t equal to 2e to the negative 2 minus e to the negative 2, e to the 2t. You can simplify a little bit more if you wanted to. 2 minus t, e to the 2t minus 2. And any of these are fine. It doesn't really matter. I mean, these are fine solutions right there. Okay. So that's that's basically how you solve that. That's when you do these problems, I'll give you the question, most likely tell you what type of solution is, or how to do it, or at least not how to do it. I'll tell you where it came from, what section, or give you an idea, which type you're going to do. I'm not, you got to realize that if it's a repeated root, then what you do. I won't tell you that. But distinct roots, how to solve it, but you'll know it's kind of from this basic sections because there's just so many different methods we're learning. All right, so the next thing I want to look at, we'll go ahead and break. It's a good place to break because we're going on to 4.3, and we want to talk about complex roots. And then I've already posted the notes, so hopefully you've already seen them, but we'll go through it. And then we get into 4.4, which is basically, then we do the non-homogeneous case not set equal to 0. Okay, here we go.